So I'm gonna just drop it in words here, and then I'll do like a more detailed walkthrough and diagrams, right? So basically what happens is when we have energy, right, that is absorbed and that is equivalent to a particular wavelength of light, we're gonna see the complement of that color or the opposite of that color. So if we have something that absorbs a lot of green light, then we're gonna end up seeing purple, right? And we're gonna talk a little bit more in detail about that. But let me just start by just dropping this equation here and asking you guys if you remember this from module 1. Do you remember this? They call it the Bohr equation. E is equal to h times frequency. And this is just your Planck's constant, right? Remember this from module 1? Planck's constant, right? And then this curly V is gonna be your frequency, right? So when the energy now is absorbed, this frequency V corresponds to a particular wavelength, right? So the speed of light, C is equal to lambda, what is that? Lambda times frequency, right? So the frequency is gonna be equal to the speed over lambda, right? So when the light absorbs a certain amount of energy, right, there's a certain frequency that's associated with that particular energy. And so, AKA by extension, there's a certain wavelength, right, that's associated with that wavelength of light that's associated with that said frequency and energy that gets absorbed. So are we good up to that point? I don't want to lose anybody at this point, because this is very key going forward. So this is going to be your wavelength of light that corresponds to a set frequency and that corresponds to a certain energy, right? So when the energy is absorbed, that's a particular wavelength of light that it's absorbing. We're going to see the complement of that color. We're not going to see we don't see the actual color, so when we see something purple, that doesn't mean that it absorbs purple light, it means that it absorbs green. We're seeing the complement of what's absorbed, right? And I'm gonna just do a quick sketch to show you what that looks like on a diagram, like schematically, right? So these are your equations, key equations. Make sure that you remember these ones, okay? So remember your delta E is equal to h times frequency. And remember that the frequency can be rearranged to be just the speed over lambda, right? So remember that from module 1. That's important, right? So I'm going to clear these drawings that I did right there. And I'm going to just do a schematic to show you, right? So if we look at titanium, that's our transition metal, right? That's our first one that we spoke about. We have titanium 3+, right? So the way that titanium absorbs, they appear purple, right? But it absorbs green. So what you have is, say you have your solution, you have your little flask, right? So you have a flask with your titanium ions in it, right? Ti3+ in it. Then it absorbs energy. So that's your delta E is equal to HV, right? And this frequency, right, corresponds to a particular wavelength, and the wavelength of light that we were able to this solution absorb would have been like, all of these are going in violet, blue, green, right, yellow, red. So you put all of these lights are coming at it, right? But then once it absorbs, you can correlate that frequency back to a particular wavelength, so you will know what it absorbs. So it actually is just only gonna absorb the green, right? And that's because of this idea of quantized energy level. It can only absorb a certain amount of energy for transitions. Different transition elements absorb different amounts of energy. So titanium in particular will absorb green, right? So whatever the energy transition or the energy changes that's associated with green, this frequency, we're able to correlate that to a green light. So the titanium absorb greens. We're putting all these colors at it, right? But only the green has the energy that's needed for the color transition. And so it absorbs the green, but it allows all the other ones to pass through. So it sucks in the green, you know, and then all the other ones that it didn't absorb, those are transmitted, right? So those pass through it. And so red, what passed through, right, is going to be red, blue, and violet. And so when we look at it with our eyes, we're going to see that as a purple color. So that's why it appears purple. Right? So that's how colored ions, that's how we see them as the color that we see them. And this is a very important part to grasp. So make sure that you grasp this clearly. Okay. So just to recap, we have a solution. The solution absorbs a particular amount of energy, right? It's not going to take all of them. It's a specific quanta or quantized energy that it will absorb, a fixed amount of energy. And the energy that corresponds with this titanium compound based on its structure is that of a wavelength of what green light would be, right? Green is around 500 nanometers. So when you do your calculation, right, and you do delta E is equal to HV, right, the frequency that you get, that's going to correspond to a lambda, right? Because lambda is going to be equal to what? C over V, right? So when you do that, the lambda that you're going to get is that of a green light, which is 500 nanometers. So that's why it absorbs green. And because it absorbs the green, it allows the other ones to pass through it. And what we see are the ones that pass through. So that's why we see purple when we look at this with our eye. Okay, does that make sense? So we're not seeing the actual wavelength of light that it absorbs or that color, we're seeing the complement of it. So the ones that didn't get absorbed. So if that whole discussion was okay for you, just drop yes in the chat. And then we're going to take it up a notch now, right? Talking more specifically about the transition, the orbital transitions that cause the color to come into being. So this is just the ground level now, right? We're going to go up a little bit now. All right. So we have that. We have
So we know that it absorbs green by calculating the frequency.
Yeah, that's how you would do it. So it's either they're going to give you they're going to tell you what frequency it absorbs, and then you can go and be like, okay, that would correspond to a lambda of 500, which would be a green light, right? So it's going to absorb green, and all the others are going to pass through. So what I see would probably be purple, the complement of it, right? So look, this goes through, and then what's left is the red, blue, and violet. So when you look at that, that's going to look purple. So if they give you numbers, yeah, that's how you're going to calculate it. Or maybe they'll just tell you upfront that it absorbs green. And then you'll be like, okay, well, if it absorbs green, then it's going to transmit the other ones. And it's what's transmitted that we see. Okay? Not what it absorbs. What it transmits is what we see. Is that clear?
So does each color have a complement?
Let's see. I wouldn't say it has like a definite like okay, the opposite of green is purple. Like I wouldn't say that. But what I would say is that it's whatever is left, and then whatever how those combine together is what the eye will see. Right? So I wouldn't say the complement of red is so because like look at it. If this was to absorb red, right? You say it absorbs red. Say it's a transition ion that absorbs red, then all these other ones would pass through it. Right? So these other colors would pass through it. So maybe what you would get out is when you mix all these colors, what would you see? That's what we mean by complement, right? So when we say complement, we're not saying that it's exactly the opposite color of it. We're saying it's like, okay, it's the what's left or what was transmitted. When you mix all those colors together, what is your eyes gonna see? Do you see what I'm saying?
Yes, miss.
So I wouldn't definitively say, okay, the opposite of green is purple. Like you can't say that definitively, but what you can say is that, okay, whatever is left, whatever is transmitted, those are gonna smash together, and that's the color that we're ultimately gonna see, okay?
Yes, miss, clear.
So that's what it is. So, okay, so we're gonna talk about what causes the color with respect now to our toolkit that we have in chemistry that we've been developing all year or from the beginning of the year, which is this idea of orbitals, right? An orbital theory. And I think that this part is very interesting stuff. And I'll definitely say, definitely make sure you have a decent grasp of this stuff that I'm going to talk about now, even as you go into unit 2, because this stuff is the cornerstone of spectroscopy, right? Of UVV spectroscopy, that is. So let's talk about, we're gonna go through it methodically. So again, we're talking about our titanium and we're using that as our example, right? But we can extend this to any transition element, right? So we're talking about titanium now. When titanium is in solution, it's bonded to like a definite amount of water molecules, right? So you can have a titanium water complex that's formed. And so that would be like Ti3+, and that would combine with water. And so you get a complex, right? That's when you put the ions in water, like you're dissolving it kind of thing. You would have the titanium water complex. So we call this thing a complex, right? And so the water is what we would call a ligand, right? Ligand is what we would call the water molecule that's attached to it. And ligands, let me see, I have some definitions on the other slide, but didn't want to quite go there as yet, but let's see. Okay, let's do this. Let's do these definitions and then we'll go back to the orbital theory. Okay, so we're talking about our Ti3+, as I said just now. So we have our Ti3+ as our example. We dissolve that in water. We're gonna get a complex ion that's formed, right? And in this complex that's formed, within that, we call our water our ligand, right? And then the Ti3+ is, of course, just our transition metal ion, right? Transition metal ion. We've been talking about that all afternoon. So that's our transition metal ion, right? All right. So just some definitions now to make sure all this on the same page. A ligand, ligands in general are compounds that have one or more lone pair, and they can attach because they have that lone pair to give, right? So that lone pair is gonna be given to the transition metal ion. So they'll end up becoming attached to each other via what we call a dative covalent bond, right? And this idea of a dative covalent bond comes from unit 1, from module 1. And this is basically just saying that the ligand, you see that ligand in this case is water. That ligand is gonna be the one that gives all the electrons to the bond. The ligand gives all the electrons, right? The lone pair electrons to form that bond. Because the ion is deficient, right? The ion is deficient in electrons because it gave away its electrons. So this ligand is coming in, it has a lone pair, and it's just gonna donate all of it to the transition metal ion. And when it does that, we say it's a dative covalent bond that's formed, right? Remember now, traditionally, covalent bond is just you're sharing, right? You're sharing electrons, but when it's dative, only one of the things in that complex, aka the ligand, is donating all of the electrons, okay? So the ligand can have one or more lone pair of electrons to give, and it's gonna give it completely to the ion that it's bonding with. And so, how many lone pairs does water have again? How many lone pairs?
Miss 1.
one, let's see. So we have oxygen. So let's just sketch that real quick. So we have HOH, right? And then the oxygen is what? 2, 4. So the oxygen has 4 around it, right? Because it has 4 in its valence. Wait. Oxygen is 16, right? Oxygen is 16, so it would be 2, 8, 6. So oxygen has 6. 1, 2, 3, 4, 5, 6. Let me draw that more clearly. So we have oxygen, and oxygen has 6, right? 1, 2, 3, 4, 5, 6, right? So 1 is gonna bond with 1 from here. 1 is gonna bond 1 from here. So let me show that. So these 2 are gonna be shared, and then these 2 are gonna be shared. And so we have this 1 lone pair, okay? So that's correct. We have 1 lone pair from hydrogen. So what hydrogen is gonna do is it's gonna give away that lone pair to the titanium. And so that's when it does that, it gives completely its lone pair, then we say that's a dative covalent bond. So there's a complex that's gonna be formed. So let me erase this stuff. So the complex ion is what's formed when the transition metal ions and the ligand combine. So this whole thing here, right? The titanium and water, we'd call that a complex ion. So this is our complex ion. So we're just all getting the terminologies right? Complex ion. Let me see if there's any other definitions I wanted to talk about before we, okay. So this is kind of where we are now, degenerate orbitals and the splitting of those. So I'm just gonna take those off and then we'll talk about it now by drawing the orbitals. So remember now, the key thing or the cool thing about these transition elements is that, oh, now we're in the D block. So now we're working with D orbitals, right? And D orbitals are cool because they can do things that maybe the S and the P couldn't do before. And that's what gives these transition elements a ton of their characteristics that we see, right? So let's talk about the D orbitals now. So we have the 3D orbitals when it's like an isolated transition element ion. So like when we have just Ti3+ by itself, right? We have our D orbital. So we have our 1, 2, 3, 4, 5 of them, right? So then we have these are our 5 D orbitals, right? So D orbitals, remember there are 5 of them. So when we just have our isolated Ti3+ by itself, we have our 1, 2, 3, 4, 5 D orbitals, right? And they all have the same energy, same average energy. And then because they have the same average energy, so they're at the same energy level is what we mean, we would say that those are degenerate orbitals. So just make sure that you keep note of that, you know that you write down this term, degenerate orbital, right? And of course, I'm going to send you guys the recording afterwards too. So just write down the things that stick out to you as key points, right? You don't have to be rushing to write down the whole thing. But just make sure that you have this jotted down somewhere. Degenerate orbitals are what we call orbitals that have the same average energy, right? So when the titanium is by itself, we have degenerate orbitals, they have the same energy, right? Now here's where it gets interesting, right? When we have a ligand, right? And let me just give you some other examples of ligands that we're going to encounter throughout this section. Water is a ligand, right? Ammonia is a ligand, right? Chlorine is also the chloride ion is also another ligand, right? And then there are a bunch of other ones that we'll talk about. But for now, let's just think of water, ammonia, we have our chloride ions, right? So, okay, back to down here. We have our transition metal ion, Ti3+. We have our 1, 2, 3, 4, 5 degenerate orbitals when it's like by itself, right? It's not complex. Now we add in a ligand into the equation like water, right? So remember, the water is our ligand. It's the thing that's going to give away its lone pair, right? You see, when that happens, when the ligand comes into contact now and starts to give its lone pair of electron to this titanium, what we have is a splitting of our d orbitals, right? So we're gonna have some of them, like say half of them. Let me just sketch this. So we have spin up, spin down. So let me just be consistent. Let's just say that we're using an element like copper, right? So where we know the configuration, we kind of know how that looks and the uniqueness of that, where we're looking at copper, right? We know that we're gonna have all of them filled for copper. So let's draw copper like this, and of course, because it's Cu2 plus, so what's gonna happen is we're gonna end up having 1 in this, because 1 would have already gone, as well as the one from the 4s, right? So your 4s1 would have been taken off. That electron would have been taken off, so that's gone. And then the other one that would have been beside it for that complete, right? A complete completely filled d orbitals is gonna be gone as well, because it lost 2, right? So if we're drawing the electronic configuration of the Cu2 plus ion, this is how it would look, like just this portion, right? Where we have 1, 2, 3, 4 of our d orbitals filled, and 1 empty one, 1 half filled one, sorry, because 1 would have been gone along with the 4s because it lost 2. That's why we have 2 plus, right? So are we good on that? 2 electrons lost, right? So 2 electrons lost, 1 from the 4s, and then 1 from a d orbital, right? That was ordinarily completely filled, right? So this is what we're working with now. So Cu2 plus, this is what we have. We have 1, 2, 3, 4, 5 orbitals, but they're still, even though 1 is not completely filled, they're still degenerate orbitals. They have the same average energy. All right. So now we're going to bring water in the mix, because we can have a copper water complex too, right? So I just use copper for ease of drawing the electronic configuration here. But you can have a copper water complex, and we do have that. And so when that happens, right, these orbitals, you see there are 1, 2, 3, 4, 5 of them, the 5 d orbitals, they're gonna split in half, right? And what you're gonna have is, let me erase these words and write it over here, right? They're gonna split, because what happens is that some of the orbitals, their energy are gonna go up higher, right? The energy is gonna go up higher to match, because of the presence of the ligand, right? So because of the presence of the ligand, you're gonna have some orbitals that are close to the ligands are gonna be pushed to a slightly higher energy level. So what we're gonna have is a deviation from the case where we had them being equal or degenerate orbitals, and they're gonna end up being a split level kind of situation that we're gonna have now. So when you have that split level, this is what that would look like, right? So they're gonna split. We're gonna have some higher than what these were and some lower than what these were in terms of energy level, right? And so we're gonna have, so we put these ones up here, right? These outer ones up top, these have a higher energy level now. So higher energy level, right? And then we have these 3. We're going to put these down at the bottom. Those are a lower energy level. So they're no longer degenerate when they come in contact with the ligand. Does everybody follow up to that point so far? Because this is where it gets interesting now with our delta E, with our energy change that we're going to have to calculate like we did just now for the colored ions, right? So again, when they combine, when the ligand moves into the place now with to donate its electron, we're going to end up with this case, right? And this case is when the copper is by itself. When they're degenerate, when the copper is by itself, the copper ion is by itself. When the ligand come into play, it's going to split them up. We're going to make some higher and some lower. So they're no longer degenerate, right? All right. So now this is what we have when we have our complexation form and we have a split level of d orbital, some high and some low, right? Now, when we have one of these electrons that can move up, because you know you can always promote electrons from a lower energy level to a higher energy level, when we have one of them moving up, right, that's going to correspond to a delta E, right? Because we need a set amount of energy for that transition to take place. And so if we're promoting an electron from a lower level to a higher level, that's going to correspond to a delta E, right? Which corresponds to a certain frequency, right? Which then corresponds to a certain lambda, a certain wavelength, right? So again, here's our wavelength again. We can correlate our wavelength with the frequency, which is correlated to the energy that's required for the transition from a lower energy level electron orbital to a higher energy electron orbital. So here again, our delta EHV comes into play. We can find a lambda. And so guys, this is where the color is originated from, right? Color originated from that particular electronic transition within the complex itself. Do you guys see that now? Earlier, we were just talking about it more vaguely when we're saying how, yeah, it absorbs this and then it transmits this. But we're talking now about, okay, within a particular transition metal, what is it that's within it that's absorbing the energy, or what does that correspond to? And that corresponds to a transition from a lower energy d orbital to a high energy d orbital. And so we can, then we're able to do our calculation as we did before, and we can find the wavelength and then the complement of that. Okay, guys, so is that good so far? Let me know if that's good for you. So we just took it up another level from where we were when we were talking about colored ions, right? Now we're talking about on a chemical level, why is it that color is coming, right? Why is it that wavelength of light is absorbed? What does that actually translate to? And how does that then translate to the color that we see? That's what we're focusing on here now, using orbital theory. So this is really the key takeaway point from this slide. And I want you guys to be sure that you grasp it, right? So that's pretty much that. And so what you will find, right, is that different ligands, so like in this particular case, it was water that caused this splitting, right? So water came close to the copper to give it its lone pair of electrons. And when it did that, we had this splitting of the orbitals in the ion into a high level and a low level. You see this particular energy, this energy here, right? The energy that's required for this transition, or the energy that's the total amount of energy that's going to be absorbed, is going to be different based on different ligands, right? So let me just jot that down so you guys have that. So different ligands, I'm just going to put this in a text box here, right? So make sure that you know this. So different ligands, right? So if it's ammonia, it's going to be different than water. So different ligands, different ligands split, right? We'll split the d orbital levels, energy levels, by different amounts. Right? So this little distance here, that the energy required to go from this distance to this distance would be characteristic of a water coming nearby. But if, say, it was ammonia, say for example, it goes up, it's split in a different way such that the energy difference between the two, the lower level and the high level, is different, then that will give you a different color. So different ligands, when different ligands complex with your ions, you're going to get different colors because the energy transition is going to be different, aka the frequency of light is going to be different, and the lambda is going to be different. So Water, different ligands split the orbital level by different amounts. So different ligands, let me just complete this thought here. Different ligands split the orbital level by different amounts. So different ligands, right? So different ligands may cause different colors to be absorbed, right? Do you guys follow that? This last point, this is a key takeaway from this slide. So different ligands may cause different colors to be absorbed. Boom. So we got that. Guys, let me know, because this is the key understanding that you need, that CAPE requires you to have, right? This is what distinguishes CAPE Unit 1 from CXC. They're just building the level of complexity and giving you more detail, right? So let me see what's going on in the chat. Let's see here. That's just a while ago. So Kiana says she understands. Dia understands. Kavi understands. Kelia understands. Guys, I love this. I love that you're understanding. If there's any point at which you don't get anything, let me know. Like, I don't want anybody to leave here not understanding anything, right? So if there's any lingering doubt in your mind, feel free to ask me about it. But I'm happy that it seems like you're all grasping this transition element theory and how we split these orbitals in the presence of ligands, and how it's the energy that energy difference is what we see as the color. Like, I love that you guys grasp that. All right. If there's anybody who has a question though, as I said, feel free to stop me. I'd be happy to just like re-explain it. So I'm gonna clear this now, guys. And we're gonna move on to, yeah, this is what we spoke about. This is just summarizing kind of what just happened. The generate orbitals or d-orbitals having the same average energy. We have the splitting of the generate orbitals on complexing, and that can be correlated then to the E is equal to HV, or delta E is equal to HV. That's what we just did, right? So that's just a little summary of what we just touched on.